Hi, good afternoon, everyone. Thank you so much for joining us here, as well as folks who've joined us online. We are the Crowdflow team, and the problem statement that we've been working this summer is measuring fairness and equity in generative Crowdflow models. So, to begin with, I would first like to introduce you all to what Crowdflow means. So, to put it in simple terms, Crowdflow is basically the movement pattern of groups of people through geographical areas. To look at it more visually, as you can see on the map here, we have 5 geographical areas, and we could depict the relationship that they have between them in terms of flow or movement between them is depicted by the numerics, which are basically the flows. Now, these movements of people can be translated into crowd flow data, which would look something like the table that I have here, with each row having an origin, a destination, and a flow. And by flow, I mean that the total number of trips that were taken between that origin and destination pair. So this this table is one of the most basic forms of crowdflow data, which can be taken as input into various other crowdflow models. We could also mix that up and add more information to this data, such as demographic information or points of interest information for various geographical areas based on what insights you want to gain from this data. Moving ahead, this data obviously has its applications. And to understand the applications a little better, we can take an example of organizations such as the Puget Sound Regional Council, the PSRC, who are a metropolitan planning councils, or other transit or planning councils who could make use of this crowdflow data to take public transit decisions, such as the location of bus stops or what routes are better suited depending on the area and the need of that region. They could also make use of this crowdflow data to improve traffic management or even to forecast future transportation needs. Crowdflow data can play a really important role in allocation of resources in various areas. Now, all this data, where do we get it from? So to name a couple of resources from where this crowdflow data can be generated, one of them can be the public transit systems. Here in Seattle, if any of you guys have taken the link or you've gone in the bus and you've used your Orca card, whenever you tap that, a trip data is generated, which allows which allows um, which allows us basically to get information of how people are flowing through that public transit system. You have your GPS data from your mobile devices, which allows us to have information of people's movement in real time. Or we could consider IoT devices such as your Wi-Fi access data points or your Bluetooth beacons, which also help us to get insight to track presence of people's movement in specific areas. And well, our social media sites where we have geotag pictures where you can gain more insight into locations of people. With that said, we've had a little insight into Crowdflow and Crowdflow data. Manurag will take the presentation forward.
Thanks so much, Sakshi. So now we know what Crowdflow data is. I also want to highlight that it can be challenging to source this data due to the complexities involved in ensuring privacy, as collecting Crowdflow often involves tracking individual movements. Therefore, we need to use synthetic data that can simulate ground reality. And this is where the use for the generative Cloudflow models comes in. So the fundamental idea is generative models are trained on existing flow data that can create realistic crowd flow patterns for various scenarios. Now moving on to the next slide. So we have like so this is a family of crowdflow models that we have. So if you look on our left, we have two major models that are gravity and deep gravity. Now, all these models are in principle same. They take the flow data and generate like realistic crowd flow patterns. But they use different parameters. For example, gravity models are based on population and distance. Then we have more advanced, complicated models that use like individual travel behavior, or they use complex like temporal dynamics. So we have a wide range of models. However, for the purpose of this project, and through our conversation with stakeholders, we realized that gravity models are the one that are being most adopted right now. So for this summer and due to the time constraint, we want to focus on the gravity models. So I think there is a denying that data models or machine learning models are being increasingly used in decision making. So it is very important for us to stop and think, how do these models affect society in the long run? And there is growing evidence today that show how such models can be unfair and can even exacerbate already present biases in the society. So through our literature review and our conversations with stakeholders, we realized that crowd flow models have not been extensively studied for biases, even though they are extensively used for policymaking. So before we delve into this project, we wanted to float some ideas around what model bias is. So to begin with, we have one of the most simple biases. How we can look is like we test the model accuracy for different groups. For example, here we have like rich areas, poor areas, and we can see the model accurately predicts the outcomes for the rich areas at 85% of the time, and for the poor areas, it's 70% of the time. So the model performs good for the rich areas. Now, what this could be inferred as, model can overfit well-represented demographics in the trained data. However, I also want to bring up like fairness is not this simple and it can be very complicated and nuanced. So for this, we'll look at a very interesting case. We have our second case as well. Now here we can see like for the same demographics, we could have same accuracies. The model performs very well. 80% of the time it's accurate. But however, when we diagnose like where those 20% of time it's making error, we realize that false positives are being made for the rich areas. So by false positives means like the model is giving them better outcomes than the ground reality. So by doing this, the models could be giving more advantages to the already advantaged groups. So these are the two ways we want to look at the fairness. And thus the aim of the project is to define fairness metrics specifically for the crowdflow models to address such inherent model biases. From here on, my colleague like Purva will take over. Thank you.
Thank you, Manu. To fill this research gap, we have defined 3 research questions for us. The first one is, how do we define fairness in crowdflow models? The second is, how do we decouple any bias created by models from bias created from data itself? And the third is, how do we measure and compare different models using whatever metrics we come up with? I'll dive deep into the first question. How do we define fairness? Fairness is complicated, as Manu mentioned. It can have different definitions for different people. Also, current literature on fairness in AI focuses on classification fairness. Crowdflow modeling, as we just discussed, is not really classification or regression. It falls somewhere in between. So we had to create our own framework to define what fairness means here and how to measure it. Yeah, so to formalize our definition of equity and like to ground it in certain existing schools of thought, we focus on 2 specific theories. Formal equality is what most people think of when they think of equality. It means equal distribution across groups. What it means for us is that all location groups, so if you divide origin destinations in demographic groups, should have equal representation in data. Sufficientarianism is sort of a relaxation of formal equality in that you don't mind unequal distributions as long as they meet a sufficiency threshold. So from the perspective of allocation of resources, everyone should have their basic needs met, and some people can have more. What it means for us is that all location groups should have a minimum performance, and we only penalize you for going below that, but not for going above that. There are other schools of thought regarding equity, which we don't use in our analysis, but they're worth mentioning. Rawls and Al-Sadr talk about unequal distributions which benefit the least advantaged. And procedural justice is something which doesn't look at the ends, like the end distribution, but talks about how if the processes in which you're distributing resources are fair, then the distributions themselves will automatically be fair. Procedural justice is what typically organizations like regional planning committees or data collection organizations would be doing to ensure fairness by just making sure that the data collection is reasonably unbiased. So we also create a framework to mathematically measure this fairness, which would allow us to customize based on this equity school of thought we want to align ourselves with. So as a Crowdflow data you'd have certain Crowdflow training data through which you'll create a model, and then you'd use some features to predict certain synthetic data. Comparing that synthetic data to your test data, you'll get an accuracy metric. Now, instead of looking at this accuracy metric as a combined metric or as a monolith, we want to look at it in terms of different groups. If you were to divide your origin locations and your destination locations across demographic groups, and look at each cell as a group, which is a group of a flow that is going from that origin to that destination, and look at performance for that specific group, you can create this heat map of how performance differs across demographics. The way we define unfairness is how much does this performance vary across these location groups. So for a perfectly fair model in this scenario, you would have a perfectly flat picture, like only one color. So the performance, good or bad, is the same across groups. Taking these two sort of formalizations, we create certain performance metrics and variance metrics to define our fairness metrics. So for formal equality, we define 3 performance metrics. We have common paths of commuters, which is, you can think of it as accuracy in the sense that it only measures the magnitude of your errors. So to account for direction of errors, as Manu mentioned, good errors and bad errors, we also account for overestimation and underestimation. And the way we measure variance is through KL divergence from a uniform distribution. You can think of it as, again, the difference of that heat map with the gradient from a heat map with a flat color. For sufficientarianism, we define a performance metric, which is the difference in CPC for a particular group from a threshold CPC that we define. And we measure the variance in the same way. With that, I'll let Kiki take over the second research question.
Thanks, Apurva. And now let's move to the second question, which is how do we decouple model bias from data bias? So we developed this methodology because we realized the following truths, which is we cannot fully observe the real world movements. So actually the data we collect is biased. So we simulate this bias distribution by manually creating intentional bias for our collected data, so which is the sampling data using this sampling strategy. So in this case, the collected data became the proxy of ground truth, and the sampling data became the proxy of the collected data. So we came up with the 2 independent methods to sample our Crowdflow data. Both of them are based on the demographic feature of destination. The only difference between the method 1 and method 2 is that for method 1, we only care about the demographic feature of the destination, but in method 2, we also take the origin into consideration. So we are actually calculating the absolute value of the difference between origin and destination. Using this sampling methodology, we can get several biased samples from the collected data, and we will pass each of them to the model and train the model, and then get outcomes from the model. So basically, this is the high-level methodology of our research. Yeah, so let's move to the third question. How do we measure and compare fairness within different models? As mentioned before, we get those different outcomes from the models, and then each outcome is actually a pair of fairness index and the mean CPC, which can be considered as accuracy. The fairness index is derived from the KL divergence. And on the right side here, you can see this is an example of the heat map results of our experiment. So for each pair of fairness index and accuracy, we can plot one scatter point here in the chart in the middle. So we can also like each scatter point here represents one sample on the left. So we can also plot the edge of this bunch of scatter points. So actually, this is a trade-off between accuracy and fairness, because in most machine learning cases, when the accuracy goes up, the fairness will goes down. For each different model, we will have different edges for will have different edges. So we can compare the sensitivity of how model will be prone to bias. In other words, how each model reacts to the bias. We can observe the shape and the range of those edges to do the comparison and do some model selection. Now let's move our focus to the package we've developed to put all those concepts we talked before into action. So we developed this package, which includes a lot of functions like fetching your input data and do the train test split, and also conduct the bias sampling methodology, train and test the gravity model, and eventually do some evaluation and relevant visualizations about fairness. And also we allow users to do some customization, like using their own data or using their own defined models. For the future scope, we are considering to include more models, especially deep learning models, and also develop some model selection metrics. And we are also planning to incorporate the time series into our framework, so make it adapt for spatial temporal data. We want to acknowledge our sponsors, which include the Federal Highway Administration, the National Science Foundation Award, eScience Institute, and the University of Washington. And this is our GitHub repository and website. So if you guys are interested in it, please feel free to scan the QR code. We're still like adding documentation on it, but you can have a look. Yeah, thank you. We have about 3 minutes.
Question.
Yeah.
I guess for the group, I'm really curious about what are some of the scenarios that you want to consider in the future for unbiased? What are some of the biased scenarios that might be really interesting to explore? And can you repeat the question?
Sure. So the question is, what scenarios of bias do we want to consider in the future, right? I think right now the way that we have considered bias is very mathematical, in the sense that we have created bias based on, hey, what if you have overrepresentation of high income areas, or you have higher flow in certain areas. Maybe going forward, we would want to root that in some earlier research. We look at how this data is actually biased, look at some data sets, figure out what's prevalent, and see how our models are sensitive to that sort of bias. But yeah, thank you.
Business comes from a lot of sources like mobile device and social medias. How do you guys handle with the privacy concerning about all those data sources, especially from the mobile device and social recording in progress?
Yeah, so the question is around like, how do we handle the privacy of the data sets? So that's where these models are being used for, since Crowdflow data is private, like it involves tracking. So what we do right now is we have like some previously available data sets that are public to everyone. They have been anonymized. So we use that and we try to like make newer, like to learn the patterns. So these models are trained like to learn the patterns of flows, and they can now be applied to like other areas. So like you don't need data anymore. So you can create synthetic data now. So that this project is about. The cloud models, generative cloud models are about that, to creating synthetic data. So that's why we do not want to use this data. So they're just being used as like, you can see it as a seed. So we need a really small data sets, and we can just create like new, bigger data sets. And we don't have to like track a lot of people or like use any private data at all. Yeah.
And we are not like we are not in like favor of tracking or anything, but it's just like data that exists out in the world that is being used to make decisions.
Yeah.
And we care more about looking at, hey, you're using this, but do you actually know what the considerations of using this modeling is? And as to Manu's earlier comment, it's anonymized and aggregated. So there's no personal information at all in these data sets.
Yes. But yeah, the idea for synthetic data is like we'll be relying less and less on real data sets. Yeah. Yeah.